Graphene is super cool, or at least it was super cool. When graphene was first discovered, people expected it to revolutionize everything. Electronics, but also batteries, concrete, light bulbs, space elevators, and pretty much everything science writers could think of. Some even wrote a book on the graphene revolution. But then where is the graphene revolution? Most of this was just classic media hype that happens when a new technology is discovered. But there is a grain of truth to this story. Graphene, and 2D materials in general, are notoriously hard to fabricate at scale. Most high-quality films of 2D materials are made with chemical vapor deposition, requiring temperatures of around 1,000 degrees, toxic gases, and high vacuum. So, if you're working with anything that doesn't like 1,000 degrees, toxic gases, or high vacuum, you're pretty much out of luck with this technique. Furthermore, the process is slow, requires expensive equipment, and can only be done in batches. You can make 2D materials in a scalable way if they're exfoliated in solution, using ultrasonication or high shear to peel apart the layers layer by layer. However, constructing these films from solution is difficult, and obtaining a single layer film from 2D materials that are processed this way is even more challenging. So how do we reconstruct a single layer film from a solution of nanomaterials, and do so in a way that makes almost any application viable, and make sure that the process is scalable? Simple. We assemble them on the surface of water. By taking solutions of nanomaterials and tweaking their dispersions to balance the surface tension, the spreading force, and water solubility, we can form dense, self-assembled, single-layer nanomaterials that sit on the surface of water. Transferring this material to its final application is easy. Simply dip whatever you want into the water and pull it out coated in new material. As long as the materials can survive a quick dip in water, it can work with this process, allowing for new applications in electronics, but also industrial and biological spaces. Best of all, this process can be continuous and scalable, meaning it can supply industry demands. My research focuses on expanding and controlling this process. Using signal and image processing, I'm digging deeper into the physical dynamics at play when the film is forming, examining the fluid dynamics, interparticle forces, and jamming transition present as the film forms. My goal is to then use this understanding to print nanomaterial heterostructures on the surface laterally itself. This is the first step in creating a multi-material nanomaterial printer that prints in single layers and can be used with any application.